Well, good afternoon and welcome to webinar number 8, which is about 3D modeling and printing with NCLab. And we're going to learn how to use the course, the app, and the printer to build great 3D models. I'm Sheila Crawford Bunch. I'm the Director of Education for NCLab. And this webinar series is made possible by a Nevada State Library Archives and Public Records Continuing Education grant funded by the Institute for Museum and Library Services through the Library Services and Technology Act. For those of you who are not familiar with NCLab, we provide a self-contained desktop platform where you can learn and use computer programming, modeling, and many other STEM skills. You learn through self-paced, self-graded courses, and by that we mean that each course is divided into a sequence of levels where you are taught a skill and you immediately get to practice it. You solve a puzzle or a problem or create a model and submit it for evaluation, and you get instant feedback on how you did. So that's the self-graded part, and it's very helpful. You can walk yourself through a lot of knowledge that way. Once you've learned some skills, you can apply them using the apps in Creative Suite, and the app we're going to focus on today is the Plasm app under 3D modeling. And that's where you also put it to the test. You can design, export, and actually print your 3D models. So this is what we're going to learn today. We're going to start by just taking a peek at what 3D modeling is being used for. Look at the main type of printers and materials, actually the processes that you're likely to encounter in a school or a library. We're going to talk about managing expectations. You know, people see spectacular models on the internet and expect to be able to go from 0 to 60. And of course, that's not the case. And so we'll talk a little bit about managing those expectations and how modeling works with constructive solid geometry. Then we're going to walk through the process. We're going to talk about how you can learn by playing with modeling. And then once you've got your feet wet a bit and are used to how the scripts work and maybe you've built a couple of things, then you can try a more systematic approach to modeling. And this, of course, is going to lead you into how you would expect to perform in the job market. We'll take a peek at the course syllabus because this is something you can use as a guide to learn specific skills, and then look at how we can design camps around building 3D models and take advantage of some of the project ideas that we already have. So how is 3D modeling being used these days? In the work world, this is known as additive manufacturing rather than 3D modeling. So if you're researching how 3D modeling is being used, you might want to use additive manufacturing as a keyword. And it's literally exploding. It's being used everywhere. You can see on the far right, there's a little building that's been built with a large-scale 3D printer. It's hard to even think of it as a printer. It's like a little crane. And it uses more than one type of material. It can rather quickly build a structure that's got some very different properties than traditional construction. And then the middle picture shows a printed circuit board that is printed with a 3D printer. And on the far left is an ear that's being created as a transplant, and it's also 3D printed. Below each picture, I have put links so that if you're interested, once you get the PDF of this slideshow, you can get some deeper story on how these are all built. Those are just a few examples, but it's used in art, it's used in jewelry, it's used in food. Some of those foods seem to be joke foods, but look out, they can make a pizza in 6 minutes now using a 3D printer, so you never know where this is going to end up. You do want to encourage your patrons or students or learners in a club to use web resources. You can start with newsletters and magazines because they'll give you recent updates. And I've given you some links there that you can explore. But always check the date of the article. You might read something and go, oh, this is great, this is so new. And then you look at the date on the article, it's 2011, which is 7 years ago. So be sure when you're reading things that you check the date. And of course, the quality will vary, but there are really some excellent articles out there. Last time we were talking about communities, and again, there's just tons of information on the internet. It can be in the form of a blog. It could be a community around a printer. For instance, the Prusa printer has a great community. This is one of the reasons it's been so successful. You might be looking at a knowledge base, and we're going to look at a very good one that I found today. And the manufacturers always have frequently asked questions. If you're looking at your filament or any of the chemicals you're using, you want to check the MSDS sheets for safety information. Sometimes you can take advantage of open source software. You can find literally millions of downloadable files that you can print on a 3D printer. And the realm is huge. It's both commercial and nonprofit sites, and almost all this information is free. Look to printer manufacturers, printing service websites. So these are people that you can send a file to, and they'll print your object for you. This is great when you're doing some kind of specialized printing. For instance, let's say you wanted to print something in gold. You're not going to have a setup in your house or your school to do that, but you can send your file into a printing service and they'll print it for you and send it back. There are good materials websites, and again, like I said, these are really fantastic 3D libraries in just about anything you can imagine. So I want to look at 3 printing processes because I think there's a bit of an intimidation factor here. You get this machine and you really don't know what it's going to do, and sometimes the initial results are a little bit frustrating. And so I did want to look at 3 processes you're likely to encounter. And there are all kinds of machines that are built on these processes. So if you understand the process, you understand a little bit about how the machine works. The first one is fused deposition model, and these are your maker bots. This is anything that, I always think of it as plastic spaghetti. It's got a filament, it melts it and drips it onto a little platform, and that's how you build your model. The second one is selective laser sintering, and the third one is stereolithography. Some of these are still mostly in the commercial range, but they're starting to hit the desktop, so you're likely to see them. So let's look at these in more detail. Okay, our first one, fused deposition model, and this is going to be almost all the printers you initially get at a school or a library or even at home, and that's your plastic spaghetti printer. The name of the process is actually called material extrusion process, and how it works in the gray box on the left is that a spool of material is fed into a nozzle. This is then melted, and then the melted material is extruded onto an XY build plane. So remember, at 3 dimensions, you have an x-axis, a y-axis, and a z-axis. And the XY plane, you're just going so far in the x direction, so far in the y direction, and that little print head will jump around all over the XY plane, forming a layer, and then the whole plane moves, and you build the next one, and that's how you get that 3rd dimension, or the Z dimension. Advantages, well, these are inexpensive and they're readily available. You can buy an FDM style printer for a couple $100 with obviously limitations. It usually has a very small bed and may accept only certain materials. There is really a wide range of thermoplastics, and thermoplastics, of course, the thermal comes from heat, and that's what you're doing is you're melting the plastic. So these are all meltable, and this is good for rapid prototyping. It may not make the prettiest model, but you're going to get your results quickly and get an idea where you are. So from an engineering point of view, that's useful. Disadvantages, well, the details tend to be a bit limited. Your dimensional accuracy, so it's your length and your width and so forth, are not great. If you're making precise parts, this may not be the method to do it. You have some problems with warping and adhesion. Remember, you're melting plastic and dripping it onto a plate. So what can go wrong there? You can have a minor variation in temperature, a little bit of variation in the material, maybe your nozzle's clogging slightly. So these can all cause you problems. And then because this is melting plastic, you need support structures. So you can't just build any old shape without building a scaffold to support it, or you'll just end up with a pile of noodles. And we're going to take a look here at this link. And this is one website that it's 3dhubs.com. I really like it. This is going to tell you everything you need to know about FDM 3D printing in much more detail than what I've said. And you can see they start out by putting it on as a type of 3D printing. So you can see there's a lot of other types. And it describes it, and it has some really nice drawings showing you how the print is built. It describes each step, a little model of what your print head looks like, your extrusion head, I should say, and how the part is built. Some of the parameters, remember these are values that you can put in when you're building your model, and there's limitations on the printer end, but then you also can tell it how big you want it and so forth. Some of the problems, so this tells you in detail how warping occurs and what it looks like. And there's a nice photograph showing the example. And it also talks about any issues with adhesion. So that's how well one layer sticks to another. So this is again some more diagrams, and this is showing how when you build the model you can actually see the layers, and it's talking about how you need support structures, how you might infill a shell. So there's 3 different examples. This is an open infill, and this is a much more dense infill. Some common materials, and these are put on a diagram here. So it shows, for instance, this is an increase in printing temperature, performance, and cost going this way, and what you might use these for, and a little bit about the structure. Is it semi-crystalline or is it amorphous, which is just like a gel? So lots and lots of information. Characteristics, the advantages and disadvantages of each one. And post-processing, this is something that people often forget, is that you're not done when you take the thing off the printer. You may have to work with that piece afterwards, so it tells you what you can do. And then 3 benefits and 3 limitations of FDM, and some design guidelines, and just some quick rules of thumb. Oh my goodness, so much information. I really like this site. I think they're a printing service, but wow, they've done an excellent job. So this is again this wonderful internet of ours, reminding ourselves just what a rich resource it is. Okay, so here's an example. I'm just going to go full screen again. There we go. Here's an example of 3D Benchy, and this is just a model someone developed some time ago that is used to test 3D printers. It's kind of fun, but it has a lot of serious attributes that are used to calibrate your printer and also troubleshoot it. You can see it's got a lot of interesting curves and shapes and holes and so forth. All these things are measurable. And you can also find sites that will tell you, well, what happens if my benchy comes out like this or this. And so at the bottom here, I've got a couple of links. You can download a benchy file for testing. And this particular article goes into some of the things that happen with FDM prints, some of the problems. Okay, so the second process I want to look at is the selective laser sintering process. And there's some real advantages to this. Right now you're not likely to see it in a library, but you will see these at universities or some of the junior colleges as well. They're fairly expensive machines, but this is something you might want to partner with them on because there's some advantages. How this works, this is a powder bed fusion process, and it's a layer of powder. So it's spread on the build platform, and then a laser sinters, or kind of welds, the parts that are going to form the model. And as you're building the model, the unsintered powder is still there, so it's acting as a support material. Once you're finished, you more or less shake it off, and then you can go rinse your model as well to clean it a little bit better. But that unsintered powder can be reused, so it's quite efficient. And because you got this powder that's surrounding your model, it means you can stack a bunch of models. And so you can batch process several pieces at the same time. It's not just laying them out on a bed like we did with the pendants, but you can stack them vertically. You can build any shape because you don't need these extra support structures. Your unsintered materials acting as a support structure. And it has good mechanical properties because it's very evenly printed and there's no stresses on it as you're printing. And finally, the surface is a little rough, as water absorbent, and that can be dyed. So you can take your whole batch, you can dump it in a dye bath, and color the objects. So what are the disadvantages? Well, right now it's an industrial-only process. One company, Forum Labs, has been promising a benchtop version for some time, and I just visited the website, and it's still on the pre-order stage. They don't have it to market yet, and you're looking at $10,000 for the benchtop version. There are safety concerns. This is one of the reasons why it's so hard to develop a smaller version. You're dealing with powder. Powder can be inhaled. We don't want that. And powder and heat can also, it might explode. So there are some safety concerns. If they're going to try and get something out to market that is not used by expertly trained people under highly controlled conditions, they really have to work out those safety concerns. So these are some of the problems they're working on. You may have problems with holes in your model. Over sintering can close those up. So as it's gluing things together, it might close up your hole. You may need that hole to get rid of the unsintered powder inside, or for other reasons, part of your engineering design. So just be aware of that. You can either make them slightly bigger, or you might have to drill them out later. And it does have a bit of a problem with flat shapes. Those can work. Again, 3D Hubs has a great knowledge base on this. We'll take a quick peek at that. So same format, it describes the process and shows you how it's built. And you can see this is the powder, and it's being given out to your print bin, and you can see how this model is forming inside. And there's your laser. There's a little mirror, and it's shooting down the laser to do the sintering. So there's another view and all kinds of extra information. There's some examples, and these are vat dyed, hot bath dyed. So, and some of the issues, of course, and types of material. So there's all kinds of material. You can get carbon fiber filled nylon, so you're getting the advantage of carbon fiber, for example. So there's all kinds of materials that will give you different properties. Talk about the post-processing, and again, benefits and so forth, just like they did with the other material. Okay, so here's our benchy friend again, and I like this picture because it shows you that advantage of bin processing. You can see how all the little boats are stacked really closely together. So you could use SLS for producing small runs of an item, and there's all kinds of software that you can use to help with packing. There's a link here to the guy that actually produced this photo, and he's sharing his code, how he packed it, and he's involved in this Formlabs desktop benchtop printer that the Formlabs is developing. So this is the advantage of SLS. All right, the third process, SLA, this is stereolithography. And how about a new tooth? So I always think of ways to remember these things. Well, I know last time I went to the dentist and I got my new crown, they kept putting some resin in, and then they would take a light and they would harden it. And this is kind of how the process works. And actually, this is one of the methods used in dentistry to build prosthesis or artificial teeth. It's a vat photopolymerization process, so it's using light to harden. It starts with the liquid. So we had the first one was a filament that you melt, and the second one was a powder that you sinter, and now we have a liquid resin that you're hardening. The large industrial machines use a top-down process. We'll take a look at that in a moment. And there is a desktop version, and it's what's known as a bottom up. So it builds it a little bit differently, and you'll see in the pictures that I'm going to show you here in a moment that it requires a lot of support material to build that. So what are the advantages? It's good for small parts. It's got high fidelity. It looks really nice. So it's good for a visual prototype because it's a good looking piece, and it's a fairly fast process. Disadvantages: it takes a lot of work to get that support material off. You have to actually remove it by hand, and then it's because this is a resin that uses UV light to harden, it's also sensitive to UV light after it's finished. One of the post-processing methods is to expose it to a bit more light to increase the hardening, but then after a certain point that makes it brittle. So it's just like things you leave out in the sun and you come back and you pick them up and they've shattered in a million pieces because they become brittle because of the UV. So this is a problem that it degrades over time with exposure to light. Here again is 3D Hub's take on things. So they explain SLA as vat polymerization process and go into some detail, and there's your model, and you can see it being pulled up out of the resin. This time it's being treated from below. Remember in the SLS process it was treated from above. So this is being pulled up, and there's another view. It describes the two different methods, the top down and the bottoms up. You can see the difference there. Again, the advantages and disadvantages, and here's a good diagram of the difference between the support structures. This is the top down, so it's got a fairly small support structure underneath it, and this is the bottom up version. The supports are quite extensive. Again, there's quite a lot of post-processing, and here's someone with some snippers cleaning off the support structure. You do have an issue with curling, which is similar to warping, and it talks about post-curing, some common materials, including dental resin. And this just shows how nicely you can finish out. This is after some sanding and polishing, some spray coating, and finishing with mineral oil. There's your advantages and disadvantages again, and rules of thumb with links to other articles. Okay, so here's our benchy, and take a look at this little boat. You can see all the support materials. It's made on a desktop SLA printer, so this is a bottoms up, and you can see why it's bottoms up. There's its bottom, and it looks pretty nice when it comes out. This is a translucent resin material, so it's again quite attractive. Those are just three, and there are many, many more processes. There are machines that make very tiny 3D prints. There's a match head for scale, and there's a link to an article on nanoprinting. And on the other end of it, here is one of these crane type printers that are used to 3D print a house. And of course, they always like to create a little buzz to talk about, well, we could send this to Mars and build buildings on Mars. So maybe that'll be true as well. Expectations. We talked about managing expectations in our introduction, and this is a problem. A lot of you have MakerBots. You may have experienced something like this. It's not the problem of a MakerBot. It's usually human error, but I've seen a bit of spaghetti, and probably you have as well. One of the deals with working with machinery is, remember, you got to embrace failure here as well. These are valuable learning experiences. If it doesn't work, this is a great opportunity to see why. You can use this printing experience and combine it with a little research, and your understanding will deepen, your confidence will grow. And you may even find, if you've come up against a limitation of the machine or the process, that you're inspired to design new solutions. And this is being done all over the world. There's such an excitement over 3D printing. It's being applied everywhere, and people are working on solutions everywhere. And they could be in a library, they could be in a university, they could be at a factory, they could be in their garage. We all have this opportunity to improve the human condition through new design. If you want to see some more epic failures, I've got a link down here, and it shows some great pictures. All right, so now we get to the software. And there are different ways you can create 3D models. One is that you can scan an object, and there are machines that do this. Instructables has a way you can do it with just your phone or a camera. You're going to learn a lot by doing that. I put the link in because it's not exactly easy, but sometimes the processes that are not easy are the ones you learn the most from. You can simply download a file and modify it, or build it using a simple graphic user interface program. And these are typically drag and drop programs. I have one on my computer. It's called Microsoft 3D Builder. It's a free app. So this is something that's very readily available. And you can see I'm just messing around, and all I did was I dragged a torus for a base, and I put a square, a cube in the middle, and then I put a cone on top, and I stacked them. Do I need to know any math? Do I need to know anything? No, I'm just dragging things and building them. So very simple to use, at the same time, not terribly deep. On the other end of the scale, you can build a design using some specialized software or CAD. And there are general engineering CAD programs, and then there are softwares that are industry specific. So usually they have a big library of shapes that are useful to that particular trade, or they have some tools that make it easy. For example, if you're building a house, you can click a button and all the walls pop up. There are a lot of different softwares. Those do require expertise and practice, and they usually come with a price tag because they've invested so much time in developing these, and they're quite sophisticated. Oh, yeah, NCLab 3D modeling. So where does this fit in? Well, we're a little bit different. With our 3D modeling, you're actually learning how to think in 3D. It's not just downloading an image and converting it to a printable object and printing it where really you've taken out that middleman of building it. It's being built for you, and it's not just playing with it like a drag and drop. You're actually writing your scripts to create your objects. So because you're writing the scripts, you're learning how to do a whole bunch of things. For one, you're using object-oriented programming. Now, do you need to know object-oriented programming in order to use it? No, but you're actually using it. After you've used our 3D modeling for a while and you go to learn object-oriented programming, it'll make sense to you. You're also learning how to control the parameters of geometric shapes. Now, that's going to teach you two things. It's going to help you with math, because sometimes we learn math out of a book, but we can't really see it or manipulate it, so it doesn't make a whole lot of sense. But also that gives you a lot of power in what you build in your model. You're also using set theory. So you're using sets to combine and subtract objects and do all kinds of things to objects. And again, sets is an area of math. You're seeing how to use sets, so you're getting that visual interpretation of mathematics. And you're also learning how to see shapes the way the computer sees them, not necessarily the way you remember them from your traditional geometry instruction in school. Computers have limitations on how they see them, but you're also exploiting that to create your shapes. Lastly, in geometry is you're calculating and performing geometric transformations. That's a big mouthful. You might remember it as move, rotate, and mirror in simple terms, and officially as translations, rotations, and reflections. And you're doing that in both 2 dimensions and 3 dimensions. 3 dimensions is pretty tricky because you have a lot of axes to rotate around. You have different directions you can rotate, and so it takes some practice to understand how that works. And because you're doing them mathematically, this is really increasing your brain power tremendously. And finally, the 3D modeling program has what we call a Python wrapper. So it accepts any kind of Python into your script. And as you learn how to program in Python, which you can learn through Python 1 and 2, you can apply it. And I'm going to show you a model I built a long time ago and how I think about it now that I know a little bit more Python, how I could design it better and much more powerfully as well. Okay, so again, let's go back to managing expectations. Oh, that's a lot of math and programming. Excuse me while I go drag and drop. Okay, yeah, you just told me I'm going to have to work at this. That's no fun. Well, actually, it's not that hard to learn. The course teaches you what you need to know step by step, and you're going to get to practice each skill as you learn it. And I can tell you as a teacher, the app that my kids had the most fun with was the 3D modeling app. They got to build stuff, and when you get to build stuff, you're willing to put up with a bit of work. Okay, second expectation. My model's so simple. I just want to scan something. Yeah, it's hard to build a complex model. So just treat this as a learning experience. You're going to learn skills. You're going to get some practice in. You'll start building your ideas with the app right away. Have fun with it. Watch your skills evolve. Yes, there are going to be times when you just scan something. But once again, you're building this wonderful understanding that is very empowering. All right, argument number 3. I don't want to waste time with 3D modeling. I need professional software. Well, you will interact with that professional software much better if you have a solid foundation. I highly recommend you learn 3D modeling first, so you understand how the computer thinks, a little bit about how the math works, and then the professional stuff is going to make a lot more sense. You're going to learn it a lot faster. Let's see, when we were doing the engineering webinar, the job skills webinar, we looked at this hollow cube, and this is the default app in the Plasm program. There's a link there, and it explains how this is built line by line. This is really showing you, in a nutshell, the power of the program. So on lines 1 and 2, for example, what are you doing? You're creating objects. And these objects are calling little programs. through the keywords and providing it with the argument that creates the cube. A cube only needs to know one dimension, and that's the length of one edge, and you provide that with the argument of 2, and it inputs it into its program, and it creates a cube with an edge of 2 units. Here you've got line 3 and 4 and 6 and 8 are performing transformations, so you can see how that works. And then on line 9, we're taking advantage of sets. So there's a union of the 3 cylinders that we create, and we're subtracting them from the cube. And then we're also performing some other functions. So that's why it's such a neat little program. It gives you a taste of what's to come. All right, so when we're designing with geometry, we can look at it from different points of view. Probably the most relatable point of view is a visual one. Think back to any kind of drawing course you might have taken, Drawing 101, you might call it. And you may, or you might have one of those how to draw books, or yeah, how to draw Pokemon or something. And they usually start with some basic lines and shapes. And then once you block those out, you start to refine them by adding smaller shapes, and then you map on color and texture and shading, and voila, you've got a pretty nice looking object, in this case a hand. You want to think about your visual design in terms of polygons, and in 2 dimensions. Those are simple polygons. They can be rectangles and quadrilaterals, and what do we have here? We have a 5-sided polygon and closed curves. So these are ovals. This one is a bit of an irregular curve. It's the top of the thumb. And once you get into 3D, then you're looking at prisms and spheres and cylinders and cones. The computer thinks of pyramids and tetrahedra as a type of a cone. So a cone with only 4 sides would be a tetrahedron. So think about building your model in basic shapes. Okay, so another point of view is engineering, and this is more how it works rather than how it looks. So you're going to possibly be taking a functional approach to your design rather than simply visual. And you're going to be dealing with things like connections. So you might be breaking down your model into different parts. You can see you've got 2 different arms. These would be printed separately. I'm not sure whether they're showing just this piece rotating or if they're adding these other pieces to it to form a full hand. But then you've got these other parts that you're going to connect to. A lot of thinking here. You can see where the math comes in. These are different degrees of rotation. These are different pivot points. You might be adding sensors. You might be adding wires to control the sensors and the movement. You might be adding elastics, transmitters and receivers if it's wireless. You may need to consider clearances, so you may have to drill holes. And remember, we're talking about SLS. You might lose the hole. Actually, I think all the processes are a little iffy on holes. You need to clean up your print usually afterwards. You may be looking at fitting pieces together very closely, so you're drawing your dimensions very carefully. Again, you might be printing several pieces and then later joining them together. So keep that in mind, that engineering looks at design a little differently than just visual. And then the computer has its own way of looking at things. Images are actually stored as tessellations. It's a bunch of triangles. And there's different modeling methods. We use constructive solid geometry. As you can see, if you have more triangles, you have better detail. Again, if you want a really nice, smooth model, you're going to have an awful lot of triangles, maybe in the millions. This is going to make a slower process and a larger file. So there are trade-offs when you're designing. Do you want something that doesn't require a lot of detail, or are you going to trade up for more detail? From the computer's point of view, I mentioned Python. Once you start learning some programming skills, you can write functions with parameters and a program that'll allow you to input different values or settings for these parameters. So this is nice. Once you have a function, you can call it. Instead of writing the lines over and over again, you can call a function. and name a different object, you can see fingers are all very similar, but they have minor differences. So you might have a function that creates a finger. You might even have functions that create knuckles, and then you combine them to form a finger, but then you change the parameters slightly. So that's more advanced, but this is, you can get an idea of where you can go with this once you learn some programming, and you can have a little fun with it in Plasm. Okay, from the printer's point of view, this is where reality hits sometimes. When you're building your model, you need to think about how the printing process is going to handle it, how the materials are going to work, the size of the printer, and so forth. And regardless of the method, the three methods we looked at, these are all slices. So they're 2D slices, sort of 2D, but they've got a very thin thickness. They're built on an XY plane, and then that print bed moves to build up the slices. So what is the software like? It likes clean outlines, it likes closed shapes, and you may think you have a closed shape in your model, but there might be some really tiny difference, a gap or an overlap that you can't really see, and your slicer software might not like that. The slicer softwares like Cura they're actually pretty good. They'll ask you, can I repair your model? And you go, yes, please. And they'll fix some of those gaps and overlaps so that it's clean. Also, the slicer software is getting more and more sophisticated. They'll build in supports for you, or they might create different infillings. You also want to set your resolutions, so don't expect to have really fine detail if you got a big fat nozzle or if you don't want to spend a lot of time printing. These are all limitations, and you need to keep those in mind when you're building your model. When you first start off, you really want to mess around and play. It's like jumping in the water and seeing if you can swim. You're going to make mistakes, it doesn't matter. Just have a little fun. And certainly at the computer screen end, it costs absolutely nothing to create a file, just your time. Your mistakes are not going to blow anything up at the stage. There's very low risk. If you make a mistake, you just might get a message saying you fail. So if you can deal with that, that's not a big deal. And even if you send something to the printer and get your pile of spaghetti or whatever, a small failed printer too is not that expensive. It's not the end of the world. So keep that in mind, and you can start building. And after I learned a little bit about 3D modeling, I built myself a Pokemon. I tried to find something that was fairly simple. This is a Weedle. And I look at my code now and I go, wow, I know so much more about coding. I could rewrite this code so much better than what I did. But I sort of came up with a Weedle model with his little hat, his tail, his feet, and his eyes. Would that print? No, because the eyes aren't properly connected. None of these shapes are really that well connected to print. It was just a couple of hours of fun building a program. And you want to do that yourself. Have a little fun, get that creative flow going, experiment, try some of the skills you learn in the course. And remember good old Piaget, he studied how our brain accepts new information. We need to tie it to what we already know. We need to make sure we understand what we're bringing in that's new. You need that time and you need that space to test your new learning before you really feel comfortable with it. Okay, the other part of messing around is not just on the computer screen, but you want to mess around and play offline. So a simple box of materials, paper and cardboard, scissors, tape, glue, pencil, ruler, compass, protractor. You might want to keep the coloring stuff out at the beginning because kids will naturally gravitate towards coloring rather than building. So when you're building the models, just give them plain materials. They can always decorate them later. It gives them a feel for how you can build a model. If you build a model by hand, you can turn it around in your hands and see what it looks like when it's rotated. And that helps with visual spatial perception, which you need when you're doing that on the computer as well. And it's also a very social and multi-sensory experience, and you need that. I remember one of my favorite classes in high school was home ec sewing, because we sat around and we made all these great things, but we could we could talk. It was the only class we could talk in. And you have to give people that opportunity to just build things and talk and visit. These are important facets of learning. And once you've done some messing around, then you want to start learning a more planned approach. And this is what would be expected in the work world. So we want to train that in our learners as well. I've made a little flow chart here or series of steps. And remember, all of these loop back. So at any point, you can go back to a prior step, and it really is a more of a complex net, but we're just going to look at it as a set of steps. Our first step is to just get some ideas of what we want to do. And this is where a journal is really nice. You can store your ideas. You can draw sketches and diagrams. You can take pictures of your paper models and put them in there. You definitely want to research online because as we find out very quickly, we're not alone in our ideas. So you can really build on what you started out with and see who else has done it, what kind of technologies they use, where it might be applied. Once you've done a bit of that, then you want to clarify your purpose. What are you going to use that model for? And when we're first starting out, these typically are small personal items. They're just fun. And as we grow in our understanding, we may be looking at a more serious application. Maybe we're solving an environmental problem, for example. And at the end of each of these steps, I put this in, review. Okay, this is something we typically forget to do, but if you have time and opportunity, review your ideas with a peer, an instructor, a supervisor, some kind of third party, because that bit of reflection they can give you is going to usually help you improve your idea. Sometimes they will give you garbage advice, but you're the boss. You can throw out garbage and you can accept the good stuff, and then you can make adjustments to your ideas as needed. Step 2, now you've decided what you want to do and why, have a little bit of an idea of what it's going to look like. Then you need to break your task into subtasks. Even simple models are going to have multiple steps. There may be something that you want to do, but you don't know how to do it yet. Maybe you need to build in a spiral, but you haven't learned how to use the command for the spiral. You need to assess your learning needs and then go ahead and learn them. You also want to look for printing issues, so that's looking ahead a little bit. If you're going to make a design, does it have something that hangs way out there? Is there another way you can design it so that it doesn't hang out there? Or are you going to have to put some scaffolds in to support it? You want to make some decisions on the level of detail, how much time you want to spend on this. Are you going to spend an hour, 10 hours? Is it a team effort? How much you want to spend on modeling. If you have a small local printer, that's going to set some limits anyway. But let's say you want to send it out for an SLS print, or you're going to eventually make a batch. Those are costs you need to go out and get estimates on. So this needs to be done at this stage of the game. Once you have all that information, you need to create a schedule, because one step depends on another. And again, this is a good time to review before you proceed with actually writing the code. So then you write your script. Please take your time. Typos are a curse. Any programmer will tell you that. You might chase your tail for hours just because you misspelled something or forgot a semicolon or a colon. While you're actually typing the script, just take your time. It pays. Make sure you save your work. And NCLab, when you open the app, there's always a demo code. You can clear it and then save your file name right there before you begin. So all your work from that point on does get saved. It does auto-save. So let's say you want to preserve a script and go in a direction, but you want to be able to come back to that initial script. Make sure you create a new file for subsequent changes, because it does auto-save. And right now we can't turn that off. So if you think you're branching off, create a new file name at that point. Test as you go. So don't go write 200 lines and then start to test. Test as you go. All you need is that show command to see what you're doing. You can step through the lines and build it piece by piece. You can stop at a certain line. You can even comment out a section by putting a hashtag in front of it if you don't want it to print that part. Or you can run the whole program as it exists. but you'll certainly catch a lot of errors if you test as you go rather than waiting until it's late in the game. And then do yourself a favor, write a little descriptive comment line above each subtask. It makes it so much easier to go back to part of the program later if you need to fix it. And of course, this is a very repetitive cycle. Write script, test, comment, and repeat. Okay, the green box, this may be a new experience for a lot of people. So you're going to start by exporting your file as an STL file for printing. And you can save that in your NCLab cloud directory, or you can save it to a disk. You want to check with your printer to see what kind of media it accepts if it is not connected to a computer. So some of them take your regular USB thumb drives, others take a certain type of portable media. So see how you're going to transfer that file. If you're working with an online printing service, you can just send your STL file to them or university. Or if you're using slicer software on a computer, you can certainly import your STL file to that computer. One little tip is before you save that STL file, you might want to add a weld command to clean up your model, and I'll show that on the next slide. And then again, this is a great time to review this code with someone before you go. They can help you look for problems that you might have overseen. So here's an example of the weld command, and you can find this in the list of commands in the help menu. And it just cleans up your file before you send it as an STL file. For example, you might have made things all kinds of different pretty colors. That doesn't mean anything to an STL file. It's monochromatic, and it might help with some certain joins and so forth. So weld is a useful command to put at the end just to clean up your print. Once you have the file in the slicer program or the machines program, then this is where you select the scale. It's usually millimeters, and you're going to size your model. So usually that's a straightforward zoom function. If you're dealing with a group of people, you want to print as many files as you can at the same time. Make sure they're similar designs, and you can arrange them on the print bed. Printing takes a long time, so if you can gather up a bunch of STL files from people, do that. It'll save you a lot of headaches. You're going to select the materials and the process parameters, what type of filament, type and size, maybe even color, and so forth. And then once again, review it before you send it. You might save a lot of grief. All right, and this is what it looks like. This is when we did the pendant project. There's a bunch of different pendant designs on the bed. And remember, it takes several hours, so you're going to have to plan this into your schedule, whether you do it overnight or at the end of the day. Better if you can supervise the printer, but maybe you're going to have to take your chances and let it print on its own. And then post-processing might be something as basic as just washing it. There are certain types of baths you can soak your model in to remove support and strain material. They may be solutions that you have to be mindful of, such as alcohol. You may be trimming it with a crafting knife. Again, remember safety first. And once again, since we're out of time, I'm not going to go to the link, but 3dhubs.com has an excellent comprehensive guide to post-processing FDM parts, and they do that for the other processes as well. Once you've built your model, make sure you share them, display them. You could even put on a show, reflect on the experience, hold a postmortem, write some notes in your journal, and then jump on that horse and do it again. This is how you grow and learn and develop your skills. Okay, here's some models that have been built with NCLab's 3D model. This is a model built by a student in Silver Springs, very detailed. It even has an engine inside. It has his name on the license plate. Beautiful model. This is a submarine, and it looks simple, but this is an exact scale replica, and I used some pretty advanced skills in NCLab to build. This is a planter, and again, using some advanced skills, and I didn't show the picture with the plant in it. It's really cute. but all kinds of things that you can build with our software, and all these people are smiling, and I hope you also smile when you get your results. If you're going to teach yourself modeling skills, you can use the app itself to play with the list of commands. You can go through the course to learn it systematically, and you can even cherry pick the course if you like to learn skills using the syllabus as a guide. It'll tell you where you learn certain skills. So this is an example of the syllabus, and there's a link to the syllabus. So if you wanted to use the subtract command to make objects hollow, you could go to section 9, and that's where you would learn how to do that. There's about 50 instructional videos, and there's a link. You can go, it'll take you to the page. You can select a video to watch if you want to learn how to do a process. And then here are the list of commands, and it's a pretty comprehensive document, complete with code snippets to show examples. Oh, I see a typo we need to clean up on the slideshow. This takes time, and there's a commitment to learning and coding. You're not going to just whip this out in a one-day camp. And you're going to have to figure out how you're going to coordinate the printing because of the time involved. So I would really consider having the group manage the time involved in printing. There's nothing like being actively involved to see how to make things work. And as always, we're preparing people for the workforce, and project management is going to be needed in any field. Get the group involved. They're going to learn something about project management. We have lots of project ideas. I've got a couple of links to documents here. This is one that shows you all the projects that we have built. There's one for every level in the course, and we have the documents to help you with that. And there's a reference guide on getting your file ready for printing. So let's say we did set up a camp or a club, and here's some ideas on how to do the sessions. So in the first one, I suggest let them play with the app and the list of commands. This is your messing around stage. Have them go out on the internet, use web resources to see what's out there, explore some themes. You may want to say decide on one of the NCLab projects as a theme and have everybody do something similar. It gives them a mutual support network when you do it that way. Or you may be addressing a problem and having everyone tackle some aspect of that problem. So you can use our project guide, or again, you can go out to the web to get some resources on themes. Then you want to take a little time to learn some skills. Now, I would suggest doing building models after people have completed at least Unit 1. It's hard to build a model if you have no skills. So it's matched up with Units 2 onward or even 3 onward. I haven't really made notes on learning, but it's going to continue throughout the following sessions. So have that course tab handy and keep learning skills, mastering certain levels and so forth. It'll help with the modeling. Then we're going to get into the more rigorous modeling process. So you might have a session where you're going to create the ideas, and then a whiteboarding session where you're going to plan it, and then devote a couple of sessions to actually writing the code. For some people this won't be enough, but remember they can open up their NCLab desktop anywhere and keep working on their code. Then a couple of sessions to reviewing the model, adjusting it as needed. And this session 9 and 10 is also prep and print. So it might take a couple of sessions to get through this for your group, and they can learn in the course while they're waiting. There's always something to do, or they can save their file and make a different version of their file if they want to build on an idea. You're going to need a session for post-printing finishing work to clean up the files. They might want to polish them. They might want to paint them, for example. And then a session to share, reflect, and journal and plan for next time. You might want to put them on view at the library or the school, possibly over a month or so. So these are some ideas on how you can set up a camp or a club. Our good old kids from Carson City watching the MakerBot are over here. So this is what we learned today. We looked at some printers and materials, some of the most common methods, a bit about managing expectations, how the process works with modeling with solid geometry. We talked about how you can walk through that process first by playing with it and then using a more systematic approach. And then using the course syllabus as a guide to go and spot check skills that you may have already learned or that you want to acquire, and some ideas for projects and camps. Of course, as always, I invite you to the community page. So I'm going to unmute everyone, and if you have questions, feel free to ask. Oh, where are the videos in the last clip found? Oh, that's it. You mean, okay, let me go to my desktop here and I can show you. Okay, so if I go to 3D modeling and Plasm, and I go to help and tutorial video, you can see that it opens up a folder and then all the course videos are there. And you can scroll down through the playlist and pick a video to watch. So that's how you access the videos. And how long does it take to write the code for a 3D print? Depends on your experience, for one thing. I remember one of my students was thrilled to bits because he had made a model of a computer monitor, and it took him probably 2 hours to build a very simple model, but he was thrilled to bits. In the same time, you could have someone build something fairly sophisticated if they have a little bit of experience. So you want to really keep that in mind with the group that you're working with. If they're just starting out, they're going to do something dead simple out of basic shapes, and that's okay, and print them small. Boy, a 3D modeling code, you could easily goon out and spend 10 hours working on the code, but I give it a limit, give it a couple of hours limit, walk around and monitor how they're doing. This is, again, goes back to managing expectations. They're going to think they're going to build some fantastic character from a video game the first time out. It's not going to happen. You can have a little discussion on what they could build that's simple but fun. That's what I would do anyway. All right, any more questions before we go? Oh, you're welcome. I had a lot of fun researching all those different methods. I sort of knew how they worked. I didn't know it quite so well, and I was very happy to find that one website with just tremendous amount of information, very well laid out. So I hope you guys get a chance to use that as well. Okay, I guess we can call it a day. And we have one more webinar in 2 weeks' time. It's a little project on building puzzles. You can build simple 3D puzzles that you can print on your 3D printer. Until next time, enjoy the spring weather. Typical Nevada, it never knows what it's going to do from one day to the next, but certainly we've had some just beautiful weather the last few days, and I'm hoping that you're enjoying it as well. So until next time, I'll say goodbye. Happy modeling.